So let's begin our lecture. So today we will wrap up things on the CPU side and move on to the memory side. All right. That could work. Writing things you only can read it, but they'll complain about your code being not readable, which also can be dangerous. So we will today complete things about the pipelining, how do you have a CPU, how do you design a CPU, and then start to talk about the rest of your computer, which is the memory, right? So we would like to begin by doing a quick recap, right? So let's look at this diagram again, right? We developed the pipelining method from last week, where we can fetch, decode, execute the instruction, handle the memory, and then write back, right? And as we can see here, if you want to pipeline, it means that you have to process 5 instructions at the same time across these 5 stages, right? So what are the key issues? The key issues is if each of the stage is handling different instructions, you need to basically somehow process all of them. Fetch for instruction n, decode instruction n minus 1, execute instruction n minus 2, memory instruction n minus 3. Yeah, sorry. Write back instruction n minus 4. And only write back is the one that programmer can see. After write back, programmer should see this state. The rest is updated somehow at write back, right? To do that, we come up with the idea of like, oh, okay, then use another set of register to store this temp variable, right? So any intermediate values to be stored is in this thing called pipeline register. It saves the states of each instruction through the pipeline. Why is that okay? Because each of the register files and the PC would only reflect only at instruction and the write back. The rest, we just need to store this temp value that we can read and write internally. The keyword here is internally within the hardware. We will not care whether the programmer is aware of this or not, because they don't need to see it, right? So there'll be one set of pipeline register for the fetch, one set for decode, one set for execute, one set for memory, where each of this would store internal data that are associated with the current instruction, right? And this can be costly, but it's so useful that it's used everywhere, right? It's used everywhere. You need to store more of these intermediate values. Can cause some performance overhead, but it's not as much, right? So the benefit really outweigh the cost here. It's so important that the pipelining concept is so important, because not just the drilling sound is not coming through the microphone, right? Basically, some house next to me is drilling something. Are we good? Can you hear me?
I can't hear it.
Okay, perfect. So this can be costly, but it's so beneficial. And the concept of pipelining also is used in software a lot as well, right? A function processes certain data, you store intermediate result, feed it to the next function. These are all the same pipelining concept. It's even used in the daily life. I gave you an example of like doing laundry, right? If you look at the way, like if you watch like a cooking show, for example, another great example, what does a chef do? He or she would coordinate between multiple line cooks, right? And if you go to a fancy restaurant, when you finish a plate, or and when the cook finished the plate, you basically have multiple cooks who work together. Each one of the cook would do only things that they're assigned to do at that station to put together one single plate. Same concept, pipelining, right? Have the finished product. Well, that's for the cooking show, but in the real life kitchen, it doesn't work like that, right? But that also pipelining, right? You have partially finish things prepared before the show starts, so that when the show actually begins, that's right back. You see the results, right? You are the programmer visible state. You see the results. We also talk about this concept called instruction stall, which means that sometimes you don't have enough resources. By resource, I mean your data hasn't finished, or you're still waiting for certain things. You're waiting for the data in the memory and things like that. So you can't move through the pipeline, right? Back to the cooking show. Let's say one of the line cook. Anyone watch Hell Kitchen? It's on Netflix. It's kind of fun to watch.
Yes, my favorite. I'm watching the latest season privately right now.
Yeah, so you will see, right? There are two teams left. I think the red team and the blue team. I watch it too. And the thing is, both teams would work together. Well, not they do work amongst the same team to make sure they can do the dinner service, right? People would come in, eat the food, and make sure everything is perfect. What would happen if one of the guy stall in the team? What happened? Except for
Gordon.
when Gordon Ramsay yelled at the team members.
I was about to say that, Kawacha. Gordon
But
Ramsay
why
yelled
does he have to yell?
Because there's something will go wrong, right? If one guy slow down, the component will affect other component as well.
Right? It's the same problem, right? Because if one guy slows down his or her task, right, it means that the whole plate that are being planned to put together nicely, the timing is off. So you slow down the delivery of that plate. This is stalling, right? So let's say one component is being somehow slower. It will block the progress, right? Same concept here with instruction stall. Imagine Hell Kitchen instruction stall, right? Someone yell at you, yay. So the effect here is processor cannot say fetch in new instruction because you need to finish the first one. And what can be the cause of this? It can be that, hey, everyone wants to do an adder, right? Let's say, again, back to the kitchen example, everyone want a grilled scallop. The seafood station would die, right? Because everyone is waiting for the scallop to finish, right? So same thing here. Let's say you have a workload that needs like tons and tons and tons and tons of multiplier. You're gonna wait for the multiplier, right? Some steps will take longer than another. Think memory, right? Think you have to go to the main memory. Let's say you order steak, right? Somehow the customer, for some reason, instead of getting a medium steak or medium rare, they say, hey, I want well done. It's gonna stay in the kitchen for longer, right? Because that process, you need to cook the meat until it's well done, right? So kind of. So there's a comment that say, hey, like if you do an analogy like that, right? Gone is basically kind of like a compiler that Java does. It's not exactly compiler. Actually, it's more like I think there's no good analogy. Basically, this is like a hardware scheduler, right? And most of the time, the hardware scheduler is kind of being designed to first being somewhat simple, right? He is not yelling at your code, obviously. These are actually the key here. These are not programmer visible. So there's nothing wrong with your code, actually. Right? There's nothing wrong with your code. Your code functions properly. It's just being slow. And what we, as a hardware folks, like what we can do is to identify what are the common patterns that why are things slow so that we can address it, right? And please don't have people in your head to yell at you. That's impressive. But these are because sometimes design is unbalanced, right? Sometimes you say, hey, I think I need a lot of cache. Well, it turns out you need more compute, you need more multiplier. One good example of that is the design trade-off that the GPU do is compared to the CPU. GPU would have a lot less cache so that they can add tons and tons of adder multiplier and anything like register file. The register file in GPU is huge, so that they can support this parallel execution, right? Because the people who design the GPU know exactly what program they want to run, and they say, hey, this program demands these resources, so I'm going to add more of those. It doesn't really benefit from the cache. The way we design how the program runs, it's not going to take advantage of the cache too much, so I'm going to take away the cache, right? Not entirely, but it's a lot smaller. Okay, don't look at your mirror and scream too. That sounds kind of bad. If you do that a lot, go see a doctor, please. So, and I hope that you say that as a joke. Basically, it's close to the end of the semester, so please bear with us. You're almost hitting the summer break, and don't cry as well. You will feel better. At least once you graduate, you're gonna work hard, right? But you're gonna get paid for the hard work you've done. Over here right now, you're paying to work hard. You're paying tuition so that you can work. Once you graduate, it's the reverse of that. You work and you get paid, right? So life should be awesome. So what do we do when instructions stall? So first of all, when you stall, you need to ensure correct results, right? And you want to make sure you code the correct value of what should go on to each of this pipeline register. All right, so now we take over, we covered the topic instruction stall. Another recap is data hazard, right? We showed this code before. What are the common things in this code is you have data dependency. The first multiply generate R0 required for the second multiply, which generate R3 required for the third instruction. So basically you have dependency that's something like this, right? R6 generate results for this, R8 generate results for this. So it's a lot of data dependency. And this is really common in your code. Even after compilation, this thing would exist, right? So data dependency generate data hazard. Data hazard means that you can't really pipeline that well because you need to wait until you know the results. The safest way is to wait until you finish write back, right? So we'll be waiting for a long time until you finish write back. For sure, the register would have the updated value, right? There are 3 types of data hazard. For the purpose of this class, you are going to only run into read after write because it's true dependency. Read after write is a true dependency. It appears everywhere in all type of processor. If you look at modern day CPU, you can have write after read and write after write. The reason this exists is modern day CPU will not run instruction in the order of like instruction 1, then 2, then 3, then 4, then 5. What CPU do these days called out of order execution. Anyone want to take a guess of what does out of order execution do when you run a program? So in order would run instruction 1, then instruction 2, then instruction 3, then instruction 4, blah, blah, blah. What does out of order do? Basically, somewhat like that, actually. The reality is your code, right? Let's say instruction 2 depends on 1. And this is a load. It has to go to the memory. It takes a long time, right? So can I run 1, then 3, then 4, and when I have data back, then I run 2? Can I do that? Will that be okay? So as Nawaz suggested here, right? You cut in line. Same concept, right? So this works. So you can run things out of order. We are not going to go into details on how the hardware keep track of how can we maintain this ordering and how can we maintain the correct output. This is for the next class. That means next course, not next class, next course. So if we have enough interest in the special topic computer architecture, I'm going to talk about how we can design that. But modern day computer would run into write after read and write after write because of out of order execution. In the pipeline design that you've seen, you are going to run into just read after write. And as I said, you can wait until write back, or you can do data forwarding. So the observation is basically, well, I mean, if I need the data, right, after the execute stage, I should have the data. It should be in the pipeline register, right? So data forwarding essentially not wait until the write back, but forward the result from the pipeline internally without telling the programmer. We're not telling the programmer everything, right? Anything that looks complicated and no need for the programmer to know, we're gonna hide it, right? We're gonna hide the complicated things so the programmer can spend their brain on important stuff. How do I implement new features? How do I implement new function? How do I come up with a better algorithm? The hardware will take care of this low-level thing. So we forward the results, right, for the future instruction that needs the data. For each of these instructions, we check the source. If they're still in the pipeline and the source is available, we forward them. Right? This would solve read after write dependency. The benefit here is faster, essentially. So that's the recap for the lecture on Thursday. Now we are moving to the next topic, which is, okay, let's deal with branches. What are branches? Anyone here write code that have if-else statement? Exactly, yeah, it's if-else, right? You all write code that contain if-else statement. How many people here write code that have like 5-level nested if-else? Oh, come on, admit it. There was a time when we all do this. Nested if-else also do exist, right? But it happened. Sometimes we just like, okay, fine, we just do this, right? These are control dependent. Sample code, if A equals 0, do something else, right? Or a for loop. For loop is also a control dependence. Why is that the case? Why is a for loop control dependence? Because in assembly, you're jumping, right? The loop has condition check. Is I less than n? Or is I greater than n or equal to n? It do certain things. So the question is, okay, how do we handle branch in pipeline, right? So remember the discussion on Thursday? What does branch do to the pipeline? So let me ask this question. When do we know that this is even a branch instruction? At what stage? Decode, right? So you have fetch, then decode, then execute, memory, and write back. So you know this is a branch, right? What do you put here? It's in decode, it means it's if you pipeline, something is in fetch, right? Something is definitely in fetch. So until you know that it's a branch, you see the first problem? Do I fetch the next instruction or do I fetch the one in the else block, right? So that's the first thing. The second thing, let's say I know that's a branch. When do I know that whether I'm gonna take the branch or not taking the branch? Execute, right? The outcome of the condition check is in execute because you need to compare. You compare, is it less than 0, greater than 0? These are execute, right? Again, what do you do for instruction inside now fetch and decode, right? Last question, if I'm branching based on certain addresses, where do I know that? This one can be in various states, right? It can be in the immediate. In that case, it's in decode. It can be from a register. Again, it's in decode. But what if you have to do this address plus 10? Then that's execute, right? So that kind of depends as well. But branch can be problematic. And this is 5 stages, right? This is 5 stages. Imagine a real CPU with like 34 stages, 38 stages, with fetch that contains like 5 different pipeline stages. So it means that I'm gonna have to fetch something, right? I'm gonna somehow blindly fetch something. So that's why this is important. That's why this is important. So how do we handle control dependencies? So we kind of have this question last week. So what are the options we have? Obviously, we can stall, right? Wait until we know the outcome of the branch before we fetch, right? So this is obviously okay. You can gamble, right? Blindly guess. What would be a basic strategy? Let's say I see a loop for I equals 0, I is less than n, I plus plus. What's the likelihood I'm going to do one thing again and again and again? It's high, right? Especially if n is high. In this case, I'm going to do the same thing over and over and over and over and over again. So I guess you can randomly guess, which is basically this guess randomly. Or you can do educated guess. So in this case, what would be your educated guess? Are you going to take the branch, which is go back to the loop beginning? Or are you going to not take the branch, go to the next line? Repeat the loop, right? You're likely to say, hey, it's a loop, so I'm likely to have to repeat the loop, right? So this is the educated guess. In the MIPS processor, the processor we've been telling you to try out in a simulator, there's a thing called delay branching. Delay branching is something like this. So you have fetch, decode, execute, memory, and write back, right? And you know this is a branch. What would MIPS do is it would look further ahead and see, okay, I'll find something. I'll find something to do in the fetch that for sure, it's okay to run. So that I delay the branch. So this is what MIPS is doing. Delay branching is basically, instead of fetching the next instruction, I will find something in the future to do that I'm sure, 100% sure I will have to run it. Anyone want to take a guess on who is responsible for finding this instruction? So can I use can I use a hardware for that? Or do I rely on something when you process the program? Sorry, my cat is trying to sabotage the keyboard. So you can do this in compile time, right? When you compile the code, you know, okay, for sure I need to run this like I plus 1. So I'm gonna fit I plus 1 here, increment register. So I can do that. And MIPS actually do that. So it is called delay branching. Or you can do something else. This is what the GPU is doing. Well, GPU doesn't do this, but certain idea propose this. Switch the thread and do something else. So you context switch. Thinking of it as you have multi-threaded running. If thread 1 is a branch, switch right away, run thread 2. You do what ARM and the GPU can do. Actually, x86 support this as well. It's called Predicated Execution. It converts branch into data forwarding. So you can do data forwarding on the result of the branch. Last Thursday, I actually forgot who suggested this, but run both block. Another legit solution. Fetch both paths, right? It's called multi-path execution. So today we will go through kind of like 3 first bullet point because it's the most common, easiest for the first two. The first two is easiest. The third one is really hard to do it well, but it's everywhere. This branch prediction is so important in every single CPU. They have one. There's a prediction logic. It's so important to performance to do it well. But let's go with stalling the pipeline, right? So again, 5-stage pipeline, like here, and you stall. So I'm gonna switch the slides, right? Switch the slides and show you the code, which is this. You have branch right here. How many cycle with pipelining? If I stall, what happened? I add, right? Fetch, decode, execute. Assume everything take 1 cycle. Memory and write back. If so this is basically if R0 equals R1, go to next line, else go to immediate, right? So instruction 2, fetch, decode, execute, memory, and write back. So for now, instruction 2 is fine. Like I don't care, I'm the branch, right? If I stall, when do I know whether what am I gonna fetch? Execute, right? So with data forwarding, I can fetch here, decode, execute, memory, and write back. Fetch, decode, execute, memory, and write back. The thing is, do you know it's a branch by the time you fetch in cycle number 3? Not exactly, right? So you fetch first. And if you fetch wrong, you fetch again. With me so far? Basically, if you say, hey, I'm correct, move on. If I'm incorrect, I'll throw away what I fetch. Of course, I can throw it away. I can clear the pipeline register. It's fine, right? I'll fetch again. With me so far? So depending on the outcome, the fetch can happen again by say, hey, I'm gonna throw the old one that I fetched wrong. Right? This is similar to blindly guess, right? This is similar to blindly guess. Over here, fetch, decode, execute, memory, and write back. Fetch, decode, execute, memory, and write back. And then you guess here. You guess. And then you decode, execute, memory, and write back. So if you guess correctly, yay, I'm fine, go ahead. If you guess incorrectly, you fetch here, throw this away, decode, execute, memory, and write back. So the difference between stalling and blindly guess is particular example. Stalling guarantee that you're gonna have to wait. Blindly guess, I'm gonna take a chance. So if correct prediction, you do this. Fetch, decode, execute, memory, and write back. Fetch, decode, execute, memory, and write back. Right? What if I predict incorrectly? So what if I have wrong prediction? Then you get rid of this, right? Get rid of this. You fetch again, decode, execute, memory, and write back. Yeah, basically you kind of double fetch, which is you throw, you squash, you throw away the old instruction that you fetch a new one. All right, educated guess. Not really sure why I go back to this pipeline design, because I don't need it. But what would be the simplest form of guessing? So what's the easiest thing to guess? Yeah, I guess loop, right? But the simplest decision to guess is to always do the same thing over and over again. So you can say always not taking the branch or always taking the branch. So when I said not taken, I mean that if I see a branch, I'm not gonna take a branch. I'm gonna say I'm gonna get PC plus 4. Basically, I'm gonna get the next instruction. Right? So this is always not taken. Always not taken, it means I'm gonna always go to the next instruction. Always taken, it means that I'm gonna always take the branch. I'm gonna go to whatever things I'm gonna branch into. Why is this good? You can also pick randomly. Which one is likely to be better? Between random guess or the simple guess of picking one, like let's say I pick PC plus 4. Yeah, so if you guess one way or another and you compile the code in a way that, for example, if you run into the loop, if you have a loop, you make sure the loop body is in the PC plus 4, then you're gonna be correct more than half of the time, right? You're gonna likely be correct like maybe 60 to 70%. Right? There are actually like research paper that run program, right? The real program, and do this. I'm gonna always predict taken, and you get around 60 to 70% correctness. Right? So this worked not too bad, right? You're doing better than random, right? So if it's a random guess, probability tells you you're gonna land around 50%. If you pick one thing always, you're gonna get maybe 70%, 75%. Can we use something else? There was a paper that say, hey, this is basically the idea is for example, put the loop body at PC plus 4, so that if you always guess PC plus 4, it's gonna be the loop body. So that's gonna improve the accuracy, right? Anyone here want to guess the downside of this? Obvious downside of picking one thing all the time? Well, it's not good enough, basically. You still have a pretty relatively high misprediction rate, right? So why now that you might be wondering, okay, I talk so much about misprediction with if else, right? How many common is a if else in your code? Let me ask you this. How often do you have that? A lot. It's really, really common. Like I have to tell you, function call it's a jump, right? You have plenty of those. You have if else, you have loop, right? So it's everywhere. So the downside of misprediction, let's talk about it. Let's say you have 5-stage pipeline, right? If you stall, so let me go back to this example, which I think I did wrong. So let me go here, stalling. Right, stalling. So let me clear this up. With stalling example, you fetch, decode, execute, memory, write back. Fetch, decode, execute, memory, and write back. And because you are stalling, it means that I'm not going to even start until decode, right? Until I finish the execute. So I do this. Fetch. I need to finish execute. So fetch, decode, execute, memory, and write back. So you're not doing any useful work in the disk2 cycle. So you're stalling, you insert two no-op. Basically, I'm not doing anything in this 2 cycle. This is the 5-stage pipeline. So let me go back to the 5-stage pipeline here, right? You need to put no-op into fetch and decode because I don't even know what I'm going to do until I finish the execution, right? So let's say in a 5-stage pipeline, you're wasting two cycles. Assume this. I have 10% of your code, 10% of your code is a branch, 10% is a branch, and 80% of the branch are taken. 80% of the branch are taken. What if, okay, what is the number of cycles you take per instruction? I assume always taking the branch. So your prediction is I'm going to take the branch all the time. How do we get that number? How do we calculate this? How do we calculate this in the first place? The way I approach this is, let me first start with, assume I have 100 instructions. That's the easiest thing I can do for starter. I have 100 instructions without branch and perfect data forwarding. How many cycles do I need to finish everything? Roughly. Yeah, it's actually turned out to be 104, right? Because the first one will take 5 cycles, but then you can pipeline them all. But roughly is 100 cycle. 104, 100 amortized, it's fine. There are 10% control flow. So out of that 100 instruction, how many of those are branch? What's 10% of 100? Wait, 10% of 100. 10% of 100. 10 instruction is branch, right? How many of those are incorrect? Two of them, right? So you're wasting 4 more cycle. So basically you're changing from, instead of 100 cycle, you go 104. You go 104, right? So you're at about 4% slowing down, which seems okay, right? It seems okay for now. It's like 4% slower, it's okay. Well, actually, in fact, it's not okay, right? That's actually almost 1 generation of processor. But let's assume 4% is okay. Let me run another piece of, like, another different code, same assumption, but in this code, 10% are taken, the rest 90% are not taken. So with 100 instruction, again, right, 10 of them is branch. In this case, if I always take the branch, how many incorrect guess I'm gonna end up with? Only 10% is correct. So out of 10 branches, how many incorrect prediction I'm gonna end up with? 9, right? 9 incorrect. So how many more cycle? 18 more, right? 18 more cycles, because each incorrect decision, 2 more cycles. So over here, instead of 100, you ended up with 118. This is 18% worse, right? 4 to 18% worse. That's getting worse, right? So the typical goal of branch prediction is how can we make this better? How can we improve accuracy? Because if you say, I'm going to guess one thing all the time, right? If I guess one thing all the time, the downside is if I change my program, the accuracy would fluctuate a lot, right? It would fluctuate so much because the program would behave differently. To do that, generally, there are a few things you need, right? First thing that we need is we need to first figure out if that instruction is a branch or not, right? That's the first thing. Until decode, we don't know. Are you all with me? Basically, until the decode stage, we don't even know if that's a branch or not. Because when we fetch, we just only have the binary. We don't even know what instruction it is. So that's the first information we need to know. Anyone want to take a guess on how can we predict if that instruction is a branch or not? What thing can we look to guess? Basically, during the fetch, what's the only thing we know? Well, we don't know the opcode yet because we are in the fetch, right? In the fetch, and we want to predict if the instruction we are fetching is a branch or not. So the only thing we see at that point is which value when you're fetching. We have the PC. We have the program counter. What is the program counter pointing at? It's the location of that instruction, right? So if you run something, does the address of your instruction changes at all? So let's say I have a branch at address 10. In the next 5,000 cycle later, is address 10 is that still a branch? Yes, it's going to still be a branch, right? So one thing we can do is look at PC. Look at the value of the PC. If the last time I see this value and it's a branch, what can I do? I can predict, right, that for sure this is a branch. So once you know that this particular address is a branch, you will know for sure that in the future, whenever PC comes back to this value, it's a branch. Any questions about the first bullet point? This is the easiest one, basically. Because you've seen this before, you've seen this instruction before. If you point to that address again, like, oh, that's a jump instruction in this line in your assembly. So I know for sure that's going to be a jump, right? The next question is, do I take a branch or do I not take the branch? This is when prediction come in because we need to guess. I have if else, do I jump into the if or do I jump into the else? So this is when we need to predict. The third piece of information is, if I know I'm taking the branch, let's say I jump, what's the last information you need to figure out where do we jump to? You need the target of your jump, right? Basically, if and else, the code would be somewhere in your assembly, right? So you need to know, okay, if I take the branch, let's say if I need to jump or if I need to branch, do I go to address 54 or do I go to address 66, right? Do I go to address A10, right? I need to know what address do I jump to? Where is the beginning of that else block? So with me so far, there are three things. Is that a branch? If that's a branch, do I jump or do I not jump? Taken versus not taken. If I take the branch, where do I take it to? Where's your destination, basically? Right? Any questions so far? For the second and the third bullet, we will not talk about it for the purpose of this lecture. The reason why I bring it up, I want to make sure you are all aware that if else can be bad to your performance. So when you write code, try to flatten your program a little bit. Make sure you have like a huge if block, it's fine, but don't nest that to the point that you have a lot of if else and complex branching. It can lead to a little bit worse performance, right? So this is one of the things that we want you to understand. Things in your program. Is flatter better when you code? I would tell you more like this. If you have a flat if-else structure, it gives the compiler a lot more room to optimize the code for you. If you have a nested if-else, it would break two things. The compiler would cry, and then the hardware would cry because you need to do a lot of prediction, right? Will that yield roughly the same performance? Depends on how good the compiler is, depends on how good the branch predictor is, and also depend on how susceptible for your program to the additional stall when you do branch prediction. So hopefully that answers your question. Basically, generally, yes. Generally, it's better. All right. Quick thing, someone call me. So let me take a phone real quick. Also use O2 flag. It helps. Easy ways to actually make sure the compiler fixes it. All right. Sorry, another spam call. And also feel free to use O3, but be aware when you say O3, sometimes it's optimized too aggressively. Some of those optimization might not be fully tested compared to O2. Basically, the more aggressive you are, most of the time you won't run into any bugs, but there's like a tiny chance when you do O3. But I think with these days, GCC and G++ compilers is so good these days. So yeah, so if you are curious about the actual techniques, I'll give you one example that is being used at least according to the first author. These days, Samsung, anyone here use Samsung mobile phone? They use this technique called Perceptron branch predictor. So this is a paper back in 2001. It's called Dynamic Branch Prediction with Perceptron. Presented at HPCA. HPCA is one of the top tier conference in architecture. Basically, if you are doing computer architecture, there are mainly 4 venue. It's like, think of it as if you heard about the New England Medical Journal or like JAMA and all those things, right? Those are top tier outlet for research in medical area, right? You have heard about Science and Nature, right? Those are top tier outlet for people who do pure science and people who also do a lot of like this really advanced scientific research. If you work on computer architecture, the top tier venue are ISCA, Micro, ASLOS, and HPCA. These are all conferences where the best of the paper would go there. The paper actually got an award. After 15 years later, every year the conference would pick the paper that still make an impact nowadays. We call this a Test of Time award. So after 15 years, the paper seen industry impact. It actually changed the way we think. The paper got an award, I think I forgot the year, maybe a few years back, right? it learns the direction of your branch using correlation between each of your branch using Perceptron, which is like a mini machine learning thing, right? You assign weights to those correlation between if else and that if else. So if this else is true, you go in there, it would adjust the weight of how likely you're gonna jump in the other if else part of your code. Why Perceptron? You can't have, well, it's complex to design a hardware that has like a full-blown machine learning model. So you need something simple, but good, right? So the author was like, okay, let's use Perceptron. Assign the weights, establish the correlation, and then you use supervised learning to predict the outcome of the branch. It actually used in a real mobile device nowadays. I think a version of this is on Samsung mobile phone. So you can see that things that you learn actually. I would say everything I cover so far, every single thing, that's always a product available based on the things I cover so far somewhere. The 5-stage pipeline is old. These days, if you look at Intel CPU, it's like 30, 40 something stages. Apple iPhone these days 20, I think probably 30 by now, right? And a simple ARM processor for like a small IoT devices can be 5 to 7 to 9 stages. So we still use this technique all the time, right? There are also more advanced technique. If you're curious, let me know. I'm always like excited to talk about these things, but this is some of the things that I really have a lot of passion to like look into, build, as well as design these things. Yes, it does sound like a transformer name. Okay, so we are going to switch gear and do a recap of things that you probably by now so sick of it since the system skill class. But before we start, save my throat a little bit. So give me like maybe 3 minutes break. We'll start at 3 o'clock. I have been talking since noon on the other class. So let me chew this like throat candy a little bit. We'll resume in 3 minutes, okay? Feel free to go get water. I'm gonna go get water myself as well. I'll be right back at 3 o'clock. All right, we'll resume and talk about the next big thing other than the CPU side, which is the memory side. All right, so I'll be right back. Lecture. Now that I think everyone is back. So let's do a recap. All right, I'm gonna go through this relatively quickly because it's been, I think, the second time you've seen this slide. Memory is slow. Even the new technology is still slow, right? Writing a fast program is basically the one of the essence of what you're trying to do, including your project tree, is to hide that slow memory access, right? Project tree is do a matrix multiply, so you want to hide every time you need to access the data. You want to, first of all, make sure you hit in the cache, right? And the size of data, if you haven't seen it already, when you have a huge matrix, right, it can affect your optimization because that can make things hard, right? The key here is, can you, for example, bring things into your L1 and level 1 cache rather than level 2 caches, right? So to speed up memory access, our community, the hardware architects say, hey, we want to be greedy, right? We have fast and small memory and we want to make it large. So we put multiple levels of this memory and we put DRAM, which is the slowest one, but huge, right, at the end. And we put SRAM, which is a really fast memory near the CPU. This is called the hierarchy. And anyone remember our like 7-11 example I have in system skill, which basically means that if I want to buy milk, for example, I want to make coffee and I ran out of milk. The first thing I would do is check the fridge. If I have any backup milk, right, that's my register files. walk out. Don't do it now, guys. So many like COVID cases these days, but in a normal world where you don't have to always rely on Grab to like buy things, you would go to 7-Eleven, the closest one, right? To say, hey, I just want milk. I want something quick. I don't want to drive all the way to like Big C or Lotus, right? So we go there and get milk. If that 7-Eleven ran out of milk, it is the same as you go to L1 cache and say, hey, I don't have the data, so I have to go to the L2. That's when you go to say nearby Lotus or nearby Big C, right, to get the milk. If they don't have it for some reason, which is not likely, right, then you go to DRAM, go to the farm, and hopefully you have milk, right? It will take a lot more time for you to go to the farm than go to Big C or 7-Eleven, right? Yes, you can always, well, go to the farm and buy your milk from there, right? Don't randomly go there and milk. It can be dangerous. So the same concept apply, right? Think of data that you want to acquire as, based on my example, the milk I want to buy, right? So you have a CPU core, it demands data. The first thing is it try to access the level 1 cache, smallest but fastest. If it's not there, you can go to L2, level 2 cache. These day and age, you might have L3, level 3 cache. In a huge cluster, yes, again, agree with the comment. In a huge cluster, you might have L4, level 4 cache. You might even have this thing called embedded DRAM, which is a much smaller DRAM, but a high bandwidth, right? Then you go to the main memory, which is DRAM, right? So quick recap on caching. Basic caching, remember, what is a cache set? What is a cache set? What is a cache line? What is a cache block? You remember those? Yes, awesome. The cache set holds a cache block. An address will map to one of these sets, right? An address will map to one of the cache set. If I have an address, I guarantee that it will be go to only one of them. So let's say my address A will map to set 2, address B map to set 3. If I have address B again, it will go to set 3. How do I tell which set am I accessing? What bits? So there are 3 sets of bits: the tag bits, the index bit, and whatever. Typically, I call it byte in block. So which one tell me the cache set? The index is for the set, right? So you use the index bit for the set. How many index bits do we need? How do I get the number of index bits required? So let's say I have n sets, like n is the number of sets. How many index bits do I need to hold n sets? Log 2 of n. Awesome. The rest are tag bits. The rest after the index bit are the tag bit. The byte in block is the lowest bit that just tell in that cache block which byte are we accessing, right? And the tag bits tell what? What's the purpose of the tag bits? Identify the block we want, right? Because we need to figure out, okay, add that things in the set. Is that my data or is that someone else's data? The tag is for that. Right? The tag is for that. There are the rec map cache, which is basically means that a cache block can only go to one single location, right? To search, you check the index bit, you go there, then check the tag bits. If it's a hit, return the corresponding data. If it's not a hit, you search the next level of the cache. So my question, is that a yes or a no? let's say I have infinite size cache. Is it possible if I have direct map cache to get 0% hit rate? Actually, that's a yes for the direct map cache. It's possible, even if infinite in size. Why is that the case? Direct map cache can have thrashing, right? Let's say I have infinite cache and only access 2 address that go to set, let's say set number 3. I have access A and access B. And this is my pattern. I go access A, then B, then A, then B. I'll go to set number 3. What will happen? It's actually not deadlocked, but A would kick B out, then B would kick A out, then A would kick B out, then B would kick A out, right? You'll never get any cache hit, right? You will never in this case get a cache hit because A and B would kick each other out, right? Any questions so far? So you can get 0% hit rate even with just two addresses. They go to the same set. They have different tags. If I have A, B, A, B, A, B, A, B, draw it out, you never get a cache hit. Because when A is being accessed, B is in the cache, A kicks B. A will now be in the cache, B get access, B kicks A. B is now in the cache, A get access, A kicks B again. Never get a cache hit. To mitigate the problem, to make it less severe, what we can do is, well, improve the direct map cache by having set associativity, right? What does set associativity mean? So it's actually not for direct map cache only, right? I'll show you set thrashing problem in a bit, but set associativity means that one set can hold more than one block, right? One set would hold more than one block. Two-way means 2 blocks. Four-way means 4 blocks. Five-way means 5 blocks, right? So each tag will store the set of possible data in there. A cache block will be stored. A set would contain multiple blocks. And n-way set associative cache means that you're going to have n blocks per set. Upside, you are less likely to run into the earlier problem where you run out of things to put in a cache block. So you kick each other out all the time. Downside, to look it up, imagine you have to go search in a bigger room. So it would take a little bit more time. Right? It would take a little bit more time because you need to check the tag. You're not checking one tag anymore. You're checking 2 tags, 4 tags, 5 tags, right? You need to actually add more circuits to check those tags. It takes a little bit more time, take a little bit more area on your chip. Fully associative cache is the extreme of this. One set, everything is in there. Number of ways equal number of cache blocks, right? A cache block can be placed anywhere, and you need to do a lot of search inside the tag store to find your own data. What is a cache refreshment policy? What does it mean? So I'm gonna go a little bit mechanical here because this is like a review of last semester. What does it mean for the cache to be replaced? Basically, it means that if your cache say filled up, right, and you have incoming access, what do you need to do? You kick something out, right? Essentially, you need to find out who am I gonna kick out so that I can place myself into the cache. This is called the cache replacement policy, and this is a design choice from the hardware point of view. most of the time you hear LRU policy or least recently used. So there's a question on the chat. So what's the point of fully associative cache? It's likely to have a hit. It's much more likely to have a hit, actually. Remember our old friend translation leukocyte buffer, TLB? I mean, those things might benefit from making it close to fully associative because you want to make sure if you need to access a page, it's there in the TLB, right? So the point is you're gonna have more chance to have a cache hit, right? Again, refreshment policy is a design choice. I'm going to talk about the LRU. Least recently used is basically based on temporal and spatial locality. Anyone remember what does temporal locality mean? What is temporal locality? Question 1. And what is spatial locality? Question 2. Obviously, time and space. What does it mean? So if I access variable x, what does temporal locality mean? They're all wrong. Sorry, guys. So when you write a program, is it more likely that if you access variable, say I, you're gonna have to access again? Yes, thank you, Thomas. If you access it once, it's likely that you're gonna have to access it again. So that's temporal locality. So what's spatial locality? What does space have to do with this? Exactly. If you access X, you're likely to access something nearby X. That's why we call it spatial locality, right? Why is that the case? Let's say you have an array, A0, A1, A2, A3, A4, A5, A6. How many times? I mean, look at our project. We did exactly that, right? You access things next to each other to do matrix multiply. Right? So data stored close to each other is likely to be accessed in a chain-like thing, right? You're gonna access one after another after another. LYU take advantage of this observation, saying, hey, if you have temporal locality and spatial locality, what would be the cache block that you should kick out? It should kick out the block that has been used the least, like the least recent, right? Because it's likely that you're not going to use it anymore compared to other cache blocks. The likelihood that you're going to need it is smaller compared to other cache blocks. So it's likely to be effective, but to implement this in hardware is a little bit costly. And you cannot, well, basically implementation of a true LRU is hard. In a real CPU, one thing I can tell you is like, they implement an approximate version of LRU. It's close to LRU, so it's still effective, but it's much cheaper, right? Imagine, let's say you have fully associative cache. It means that you have to compare every single block and see which one is the least recently used, right? Basically find minimum. Finding a minimum, and somehow you also have to keep track of a timestamp as well. When did I access it? How do I do that in hardware? So it's not easy to implement this. So we have a way to approximate it. We are not going to cover it today. We are not going to cover it for the purpose of this class. It's a little bit advanced. For the purpose of this class, from the programmer point of view, from the software point of view, hardware always try to approximate the LRU policy. That's what you can assume. It's something similar to LRU. All right. So here comes the other question we have on the chat. With set associative cache, is it still possible you have 0% hit rate? What's the answer? The answer is yes. This is called set thrashing, right? Set thrashing. What will happen if there are too many data being mapped to the same set? I can share some example. I have a four-way cache. What does four-way cache means? How many cache blocks can be in my one set? 4, right? And I have to go through address A, B, C, D, and E by this pattern. And then A, then B, then C, then D, and E, and back to A. This loop. A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. Here's your cache. What happened if I access E? Which one do I get? Which one do I kick out if I use LRU? I'm gonna kick out A, right? E comes in here. Then you access A next, because basically that's how my access pattern behave. Which one do I get rid of? Now I'm gonna kick out B, replace that with A, and then gonna access B again. B would comes in, kick out C. Then I access C. So like, oh, too bad. I'm gonna kick out D, access C. So this is ineffective, right? I use LRU, which sounds good. It's just that I don't have enough room in my set to cache. So I'm gonna have cache miss all the time. In this case, even a random policy, I'm gonna kick things randomly, is better than LRU, because if you access long enough, you eventually have at least a cache hit. With the LRU policy, you guarantee you're never gonna get a cache hit. All right. So there's been also a proposal on how do we design the replacement policy. For example, there's like a paper in ISCA. ISCA is another top conference in architecture. There's a paper that say, hey, we can use a combination of LRU and random, right? And we sample which one is better for each set and pick the one that's better for now. And then we resample after, say, 5,000 instruction or 10,000 instruction, right, to make sure we adapt to the change in the code. There was a paper proposed back in 2006. There are also many other follow-up, not follow-up, but like another different proposal on how to manage the cache replacement. If you're curious, let me know. All right. So that's it for the recap. I'm gonna start moving on to the new things. We are talking about accessing the cache. We haven't talked about handling a write. Remember our thing in the last assignment in system skill, right? Where I think it's extra credit, dealing with writes. Remember that? So when the cache block is written to, the data actually changes, right? So you need to propagate the data in a high level. Basically, if you have write to L1, what does it mean? It means that if I have to access DRAM, it should have the updated data, right? Basically, that's what it means. I need to make sure I have the updated data on all level of my cache when I do the write. Otherwise, the data to the same address will hold a different value. It will hold a different value. So there are generally two policies. Write through is simple. Whenever I have a write, I write to every single level of my cache. This is what I say in the assignment from system skill. If you write everywhere. Write that block in L1, write that block in L2, and write and update the data in DRAM. Any questions about the write through policy? So basically, if we see write through, it means that I'm gonna write through all the hierarchy. Where we have the memory hierarchy, you make sure the write happen throughout the entire hierarchy. I'm gonna write to L1, write to L2, write to L3. Every single level should have this address and the tag updated with the new data. That's all. That's what the write through policy is. My question is this: do I need to do that? So let's say I have a CPU, okay, that access the L1, access the L2, access the L3, then access DRAM. And I'm going to use a different text color here. Let's say I have address X being written over into X prime. L2 still have X, L3 still have X, DRAM still have X. Right? Do I need to update L2, L3, and DRAM? If I know that the next time I want to access X again, it would first search L1. Will there be any problem? Am I gonna get X or X prime? That's the first question is, if I have the access to this data again, am I gonna get X or X prime? There's no problem here, right? Until X prime is gone, because you're gonna get X prime. Why? Because the first thing you search is L1. You gotta look up L1, like, oh, okay, is this address here? It's like, oh, it's here. What's the value? X prime. So do you need to do write through? Not really. When do I need to write into the L2? So now my next question is, when do I need to write into L2? Exactly. The only case I'm gonna need to make sure I have X prime in L2 is whenever X prime in L1 get kicked out, right? When X prime disappear, get replaced in the L1, I'm gonna make sure I write that into L2. Then when do I know that I have to write to L3? Same thing again, right? When X prime in L2 get replaced into L3, so on and so forth. This technique is called write back. Write back. It's kind of like a lazy version of handling write. Well, I know it's in the L1. I'm not gonna update the rest until I know I have to update it, right? The question here is, how can I tell that I have to update? The way you can tell is, whenever there's a write, you add one more bit in the tab. You add one more bit in the tab. This bit is called the dirty bit. Dirty bit means that if this is set, it means someone write to this block. If it's a 1, it means someone write to the block. So if the block is dirty, what do you have to do? If you're replacing a dirty block, okay, if you are replacing a dirty cache block, what do you have to do? So a dirty block means that someone write to this block, right? So if you have to replace a dirty block, you have to write to that lower level of cache. What if the block is not dirty? What can you do? If the block is not dirty, what does it mean? So just replace. You throw that block away, right? Because why? Why is it okay to just replace that block? Because everyone would have the same data. No one overwrite it yet, so it's the old data, right? No one modify it. DRAM would have the correct data, L3 would have the correct data, L2 would have the correct data, so you can just throw the block away. Yay. All right. So this is basically the concept behind write back. The benefit here is this saves bandwidth. You don't have to modify DRAM many times. Why is that the case? So let's say you do write to the same block. Basically, write from X to X prime to X double prime to X triple prime, one after another. You are always hitting in L1, right? So with write through, you are writing to DRAM every time you have this write. But with write back, you just update the L1 from X to X prime to X double prime to X triple prime. That's all. Nothing else has to be updated. So it's much lower overhead. Just add that dirty bit and you're good. All right. So as I said, on the write miss, you also have a choice, right? When you do a replace, right? do you allocate the cache block? This is the second thing you can decide. I have a write. Do I bring that data into the cache? You can skip it. So basically, design choice from the hardware point of view, you can allocate the block on writeness. It's simpler. Basically, write are treated the same as read. You bring that to the L1 cache, or you can skip. You can skip the writes right away. Right? You skip the writes, make sure it's updated in DRAM. Don't bring the block over to the cache. There are certain benefits that we are not going to go too much into detail, but think of it this way. When you write certain data, that data is already in the register file. So most of the time you don't need it. You know the CPU already have the data when you do the write. So writes are not in the CPU world, writes are not that important to performance as read. Read is much more important because read blocks what comes next. It generates data dependency, right? It generates data dependency between instructions. So you might want to make sure that the things in the cache are just a bunch of read accesses. In the normal world, in the CPU, these are not done. Basically, write would be brought into the cache, read will be brought into the cache, and we have the dirty bit for the writes. All right, so there's a question about will the data be written to lower level caches if the higher one isn't replaced? So it depends on, so if you do write back, it just depends on the dirty bits. So if you write to that address, you update the dirty bits and you then replace and write it back to the lower level. And think about it. So I kind of want to kind of live it with this, right? From the hardware point of view, we design hardware. So you can design how are we going to manage the cache? You can have a new replacement policy, new way to identify index bit to reduce collision, to reduce the chance that everything go to say set3 and set4. You can hash it. There's actually a paper to say, hey, let's hash the index bit, right? To distribute the access across all the sets. There's a new way to deal with trashing. You can even support, let's compress the data, fit that in the cache. Why is that the case? Now your 2 megabyte cache would behave like a 4 megabyte cache. Yay! Right? So you can put more things in the cache. You can also handle parallel data access, right? So modern processor, the one that we didn't discuss, the one that can run things out of order, can issue many instructions at the same time, right? As long as the next instruction have the data that can be executed. So the data access into the memory can happen in parallel. You might hear this word, data parallelism. Data parallelism means that you're going to issue memory access, 5 of them, 10 of them in parallel at the same time, right? Because let's say you have instruction 1, 2, 3, 4, 5, 6, 7, 8, and this is the load. This is the load. This is the load. Load means I want to access data in the main memory. This is an add. This is a load. This is a load, right? These 5 loads, let's say they don't have any data dependency. I know the address right away. So I can issue these 5 loads to L1, L2, and DRAM at the same time. And the CPU will do that. The CPU would keep going through these loads to make sure you have as many data access as possible at the same time. And DRAM is actually designed to handle that too. We'll talk about that on Thursday. How does DRAM handle this? Handle parallel data access. All right. The other concept that you might run into in the future even as a software programmer is called Belidy's optimal. Belody optimal is more like a theorem. It's a theoretical thing. Good to know, not on the exam. Good to know, not on the exam. The policy, this is basically has to do with What should we evict? How do we select the refreshment policy for my cache? This is for both software and hardware cache. Belly Optimal said that let's look at every block, everything that you have to consider for replacement. You want to pick the one that are going to be referenced furthest by the program. This is impossible to implement. Why is that the case? So what information do we need to predict? Because we can predict the future, right? So this is basically, if you have the ability to tell the future, you're gonna pick the one that is furthest away. So if you, let's say, design, let's say you are a software you come up with your own piece of software that utilize the concept of caching. What would be the example of that? I guess we all heard of Facebook, right? So imagine this. If you are stalking someone on Facebook, right? What does Facebook do to that person's data? They're gonna move the data to your machine, right? So that when the next time you stalk that person again, the image is located nearby, right? And let's say if, okay, you all heard about the news about the explosion, right? The explosion nearby the airport. So what would happen to that particular piece of data? What would be the group of people that are going to access that news data? It's likely everyone in Bangkok, right? People living in the area, people in Bangkok, people in around Bangkok, right? So from the data management point of view, where should I place the data? Which server should I put my data in? Somewhere in Thailand, hopefully somewhere close to Bangkok, right? This is again concept of caching, but we use geolocation, where you are on the world, so that you can put the data at the correct places. Again, caching, right? So ability is optimal means that somehow you can predict the future. And if you have to figure out, okay, I have a limited server space and I have to figure out which data do I delete and which data do I brought in. I'm gonna delete the one that's likely no one would search again in this area, right? Likely something that no one would search again. And then I'm gonna bring in someone that bring in the data that's likely to be searched, right? So that makes sense. That's it for today. One last thing, project 3 is out, right? Project 3 is out. And I have the one last thing slide here, but basically we're gonna talk about project 3. I will give you an option on whether you want to talk it here or discuss in Discord. Which one do you prefer? We have about 15 minutes. Here or Discord?
I think discussing here is okay.
Okay, one vote for here. All right, everyone vote for here. No, you cannot use C++. It's make things a little bit easier. Okay, so let's open up the floor and what can I do to help? Well, I guess project 3 is this. So basically you have mainly the main task. First of all, the first thing is do a straightforward matrix multiply, right? So that's the first task. Obviously, you need to make sure you do this. Actually, before that, there's a matrix generator. So in project 3, starter code, right? There's a matrix generator, and that's mm.c, mm.h. These are the two where you're gonna do modification. These generate metrics for you for the input as well as the reference, which is the correct. You don't have to use Git on this. Basically, you can submit the code on Canvas. It's good to put it on Git so they can back things up, but that's up to you. So you can use this is in Python, and I use numpy to do matrix multiply. If there's a bug, blame them. I'm joking. If there's a bug, let me know. That's already, first of all, there's a bug that I'm gonna have to fix for the loading the matrix. And thank you so much for letting me know that it's seg fault right now. I'm sorry about that. I'm gonna make sure this is handled sometime tonight. All right. Basically, after this class, I have one more meeting. After that, I'm gonna basically go through that. And then the one last thing slide. First, you do matrix multiply. Any questions about how do you perform matrix multiply? So this is basically just debugging most of the time. My recommendation: start small, because once you have a small matrix done correctly, the big matrix would behave the same way, right? So if you start small, making sure that works too. So the second thing is to flush the cache. This, I don't care how you do it. Just make sure that the cache originally will not have the data, right? This should be pretty simple. There's for example, Gritin already suggests on the chat, there's a cache flush function from the library that say flush all cache. You can use that. So this should be simple. Just make sure that you flush the cache so that you can measure the performance later. The third task is to do block matrix multiply. What is a block matrix multiply in general, right? When you do a matrix multiply, typically you would multiply this part with this part, right? So if the array is bigger, it means that the thing you're multiplying might not fit in the cache because it's too big. Essentially, it's too big. A block matrix multiply would do this. It would first separate things into block and then do this part with this part first. Right? Do this part and this part, followed by this part and this part, this part and this part. Basically, it would do one block at a time in a way that to make sure that the block would fit in the cache. So the size of the block that you're multiplying should fit in the cache. So the key here is to make sure size of the block fit in the cache, right? My recommendation, make sure you parameterize the block. Block size so that you can just sweep over your, well, don't guess. You can check the size of your cache. So you can do educated guess on, okay, if my block is say 64 elements, is that good enough? Or should I do 128 or should I do 256 elements? Once you parameterize the block size, right? It allows you to use the different size of block by just running it again. Without writing again another piece of code, you parameterize them. The block size is B, and you change the number B every time you run and test your code. The fourth task is basically, there are multiple things here. Optimize further. There's already someone emailing me like, can I do this? Row to column ordering. So one thing you can do is for this metrics, right? That would go down and down and down. This might break the cache. It might cause crashing basically because you're not accessing A1, then A2, and then A3. You're accessing A0 then A64, and then A128, right? It might go to the same set. So one thing you can do is transpose this matrix first. You transpose it so that it change the way it's ordered. So the next time you do multiply, it's going to be A1, A2, A3, and 4. Because you transpose the content of your matrix already, right? You can optimize the part where you load the matrix. You can load the two metrics in parallel. Right? So that can be done. You open two files, pthread to load both of them in parallel. You can parallelize the block metrics multiply using pthread as well, because each of these multiply it can be done independently. So you can use also pthread to do that. So this is basically open-end. The fourth part is the most open-end part. I'm thinking about having like the full score at 100, but I need to check with Ajahn Sansern and Ajahn Kanat a little bit about like policy for extra credit so that it's fair for the other project as well. So I'm gonna leave the fourth part open. Do whatever you can, except for change O2 into O3. Another thing you can do is called loop unrolling. Oh, the set file load metric is okay, and I just forgot to generate segment. Oh, okay. So I think okay, never mind. There's no problem with loading the metric. Make sure you generate the metrics that has the same size as size X and size Y. When you generate, make sure it's the same size as size X and size Y. You can change the size later if you want to test your program. Basically, the metric generator will take in the size. It generates the metrics of that size. By default, I think we have 25,000 by 25,000 or something along that line for our C program. And make sure you have the same size. Otherwise, you're going to affect segfault. My code doesn't handle anything bigger because I got lazy. My bad. So any other questions? Yes, I'm gonna upload the lecture. I'm gonna upload the video, and I'm gonna upload the annotated version of this lecture as well. I think I did for all the other previous lectures, and I'm gonna do it basically whenever WebEx generate the video. Do you have a YouTube link for the class, by the way? Did I put it somewhere? Ah. I will put it on Canvas, I'm sorry. I have uploaded that. So if you go to my YouTube channel, it's there. It's on a playlist. But I'll put a link on Canvas. I'm so sorry. Sorry. Anything else? Actually, let me do it now. Demo for in class. Thank you. Yes. Sorry, can you send me an email so that I don't forget? I'll put that a demo and I'll put it on YouTube. I'm so sorry. Can you remind me through email for sure that I'll do that for sure. The link here. Okay, the link is now updated on the syllabus. Okay, it's up. You should be able to access the YouTube video now. Did I miss anything else? I think that's all. All right, I'm gonna upload the video after I'm done with the meeting today. I'm gonna do the demo for in class after I'm done with the meeting today as well. And sorry about that. Thank you so much for the reminder. Okay, take care of everyone. That's it for the class today. I'm gonna stop recording, have I?